Hi, this is meteorologist Steve Pelletieri, and I am the Weatherman. Thanks for listening to our next installment on weathermanpod.com. And today I'm going to talk about the sun and solar activity, whether or not that activity can produce climate change and or climate trends. I've always been a big fan of the Twilight Zone, especially in the earlier version that was back in the 1950s and 1960s. There was one episode in season 3, I think. It was episode 10. It was called The Midnight Sun. Basically, the story deals with the Earth getting knocked out of its orbit and getting closer to the sun, closer and closer. The temperature at midnight with the sun shining was 110 degrees. The oceans were drying up and everyone has basically left the city. The story goes on about the artist, an artist who decided to stay in her apartment until the very end. And her interaction with friends and neighbors who also decided to stay. And some of those neighbors were not so friendly. The weather got so hot that her oil paintings, and she was a painter, her oil paintings began to melt. So on and so forth. It was just more and more misery as time continued. At the end of the episode, we see Norma, that's the artist I was talking about, in bed with a fever. But looking outside, lots of snow outside. The thermometer reads minus 10 degrees, and Norma, who has been bedridden with a high fever, is being cared for by a doctor and a friend. The idea that the Earth is moving closer to the sun is only a fever dream. In reality, the episode ends with the revelation that the Earth is actually moving away from the sun, and the world's inhabitants are actually freezing to death. That episode has always stuck in my mind when I was young. At the time when I saw it, I really didn't like the Twilight Zone. I think life in the 60s was scary enough for me at the time. The thoughts of the Cuban Missile Crisis, nuclear holocaust, and whatever. And just to watch something on TV that made me even more frightened seemed insane. But as I've mentioned, I've always liked all things up. Space, astronomy, meteorology, aviation, even geology and hydrology. I loved it all. And this episode intrigued me. I thought about the Earth interacting with the sun and what it really meant. A few years later, I got a telescope. And we used that telescope to be able to project the image of the sun on a pan. You can't directly look at the sun, so you have to use a sort of like an angle lens, and it goes down onto a white disc, and you can actually see the sun from there. So you should never look at the sun with unaided eye or binoculars. But I noticed back then these little black areas on the sun when I was able to get the telescope set up right. When I used to have my telescope out during the day and I started to learn more and more about them, I learned that those black dots are called sunspots. Even though the sunspots were black, they just basically represented a cooler area on the sun. Anywhere cooler temperatures around the sun's surface, generally around the perimeter of these cooler sunspots, there would be violent interactions, which are called solar flares. Now, solar prominences and solar flares and magnetic storms, all about the same. And I learned more about them as I thumbed through my books at the library and in my home, and my Sky and Telescope magazine that I love so much. Today it's a different story. The sun is still there. We're still 93 million miles away from it, depending upon the season, of course. But this discussion is about the activity on the sun, sunspots, solar flares, and how they interact with the Earth's climate. Or do they? In order to really talk about the sun's relationship with the Earth, climate, and the climate of the solar system, it's just not about the planets, but it's also about the sun's total influence. Therefore, we have to get a little basic astronomical knowledge about the sun, and we will discuss some interesting facts that you may or may not know. The sun is our star. The sun lies at the heart of the solar system, where it is by far the biggest object. It holds 99.8% of the solar system's mass and about 110 times the diameter of the Earth. You can fit about 1 million Earths inside the sun. It's that big. The visible part of the sun is about 10,000 degrees Fahrenheit, while temperatures at the core reach an amazing 27 million degrees Fahrenheit. What does that mean? That's unbelievable. It's driven by nuclear reactions. One would need to explode 1 billion tons of dynamite every second to match the energy that's produced by the sun. That's according to our National Aeronautics and Space Administration, known as NASA. Now you know we're part of the Milky Way galaxy, and the sun is one of more than 100 billion stars in the Milky Way galaxy. It orbits some 250,000 light years from what we call the galactic core. That's the center of the universe and completes a revolution once every 250 million years or so. We're just a blink in that revolution, believe me. Now, our sun is relatively young. It's part of a generation of stars known as what they call population 1. And they are rich in elements of those elements that are heavier than helium. An older population or generation of stars called population 2 and earlier generations of population 3 may have existed, although no members of this generation are known yet. So our sun is population 1. That's the main feature. Now, our sun was born about 4.6 billion years ago. Many scientists think that the sun and the rest of the solar system formed from a giant rotating cloud of gas and dust known as the solar nebula. As this nebula collapsed because of its gravity, it spun faster and flattened into a disk. Most of the material that was pulled towards the center formed our sun. So it all came into a center mass. The sun has enough nuclear fuel to stay pretty much as it is right now, the same brilliance and the same heat for another 5 billion years, which means basically nothing to me. After that, it'll swell into become a red giant, and I don't think we'll be around for that or anybody here listening to this, but eventually it will shed its outer layer and remaining core will collapse into what we call a white dwarf. Then it will fade and enter its final phase as a dim, cool mass, what we call a theoretical object sometimes known as a black dwarf. Now, the sun and its atmosphere, as it were, are divided into several zones and layers. The interior from the inside out is made up of the core. There's a radioactive zone and a convective zone. The solar atmosphere above that consists of what's called the photosphere. And then above that, it's the chromosphere. A transitional region, then finally the corona. From that, we get a solar wind, which is an outflow of gas from the corona. In other words, it spews this stuff out, and it goes out into space towards the planets, towards Earth, towards Mars, towards Venus, all those things. So when we go out and we see that it's light, it's the photosphere causing the light, mainly the lowest layer of the Earth's atmosphere. It emits the light that we see during the daytime. It's about only 300 miles thick, and although most of the light that we see comes from the lowest third, or 100 miles of the photosphere, this gigantic, massive star, 100 miles, that means nothing. And the temperatures in this photosphere range from 11,000 degrees Fahrenheit at the bottom to about 7,000 degrees Fahrenheit at the top. And the chromosphere, which is hotter, is like 35,000 degrees. And it's made up of apparently a spiky structures known as spicules. I really like when they throw these numbers out of, 35,000 degrees, 10,000, 2,000 billion degrees. It's hard to imagine that these things actually exist, but they do. It's part of not only theoretical but mathematical science as far as the atmosphere and as far as astronomy is concerned. But basically, through all what I've just said to you, what I'm trying to say is there's a lot of heat, and it's generated from the sun that eventually reaches here. The sun makes heat. I guess we didn't have to go through all that for you to know that, but it's a hot thing, and it causes, just going outside under the sun, it's hot. But as you get closer and closer to it, when you break down what the sun actually is, you can see there's a lot of heat in order to make it still hot here on the Earth when it goes through the atmosphere. I guess all this filtering, as we said. So the corona sheds its light well. We know that. It's also called the ultraviolet rays, and it's the top of the super hot corona. Now, the corona of the sun generates the loops and the streams of ionized gas that the corona generates. And here's one of those crazy numbers again. Almost 1 million degrees Fahrenheit to about 10 million degrees Fahrenheit. What the heck does that mean? You can even reach tens of millions of degrees with solar flares when they occur. My point being, it generates heat. It's not a steady amount of heat. It's a fluctuating amount of heat. So when it throws it out into space, that has to change what's going out in the solar system, which is where the Earth is. Now, along with all the heat that it's throwing out, it's also changing magnetism. we could talk about the magnetic field of the sun. The strength of the sun's magnetic field is typically only about twice as strong as the Earth's, which to me sounds odd, considering the sun is so massive and the Earth is so small. They develop these things called kinks and twists in a magnetic field. And as they develop, the sun spins more rapidly at the equator than higher altitudes, and because the inner parts of the sun rotate more quickly than the surface, these distortions create features ranging from sunspots, which we just talked about, which are cool areas on the sun, to spectacular eruptions known as flares and corona mass ejections, which is basically throwing heat right into the atmosphere, right into the solar system, towards every planet that we have here. Flares are the most violent eruptions in the solar system, while corona mass ejections are less violent but involve extraordinary amounts of matter. A single injection can spout roughly 20 billion tons of matter into space, and some of that matter reaches our atmosphere. And herein lies the problem. The problem is that we're dealing with, we're here on Earth, and, you start your car, the fumes come out of your tailpipe, and you pollute the atmosphere. You heat up your home, it pollutes the atmosphere. Little silly things like that. But look at what this sun does. Millions and billions and all these things, like Carl Sagan used to say, the billions and billions and billions of influence that the sun has on the Earth and the solar system is unbelievable. So these are the things that we have to consider. What happens on the sun, what happens on the sun's surface, what the sun throws out is important to us. Now, like I mentioned earlier, our sun is made up of mostly hydrogen. We're talking about the chemical composition of the sun. Not super important for our discussion on climate change, but our sun is made up of hydrogen followed by helium, with all the other remaining matter of the sun consisting of 7 other elements. And the 7 other elements are the pure ones: oxygen, carbon, neon, nitrogen, magnesium, iron, silicon, so on and so forth. Still, hydrogen is the lightest of all elements, so it accounts for roughly 72% of the sun's mass. The sun is made up mostly of hydrogen. Helium makes about 26%. That's a pretty light gas, too. The Goodyear blimps, all the blimps that we see. When we used to see blimps. Actually, we should see a lot more blimps now that everybody has to stay home. The blimps go around, so maybe we'll see a lot more of those. But helium makes up 26%. 26 and 72, that's 98% is hydrogen and helium. 98%. Think of it. It's safe to say that the sun is mostly hydrogen and a quarter helium and, of course, other stuff. Now, here is where we get into the discussion of what could be producing our climate change on Earth. Sunspots and solar cycles. Sunspots are relatively cool, dark features on the surface of sun. They are often irregular but roughly circular in times. They emerge where dense bundles of magnetic field lines from the sun interior breaks through the surface. So these magnetic fields are breaking from the interior going to the surface of the sun, and they make these sunspots. So there's a relationship between magnetic field lines and a cooler solar temperature. The number of sunspots varies as solar magnetic activity does. So as solar activity varies, so do sunspots. The change in this number from a minimum of none, or relatively no sunspots except for a few little ones, to a maximum of about 250 sunspots, or a cluster of sunspots, then go back to a minimum. This is known as the solar cycle. Low to high to low. That's a cycle. When this happens, the magnetic field rapidly reverses its polarity. Here's where it gets interesting and appropriate to our discussion. When we go and we look at ancient cultures, they often modified natural rock formations or built stone monuments to mark the motions of the sun and the moon, charting the seasons, creating calendars, and monitoring eclipses, like Stonehenge or other formations around the earth from ancient civilizations. Now, many of these people believe that the sun revolved around the earth, with ancient Greek philosopher Ptolemy formalizing his what we call geocentric model, but he did that back in 150 BC, over 2,000 years ago. Then about 1,400 years later, Nicholas Copernicus described it as heliocentric, or sun-centered as a model of the solar system, which we all know actually is. Then in 1610, Italian Galileo discovered the Jupiter's moons, revealing that all heavenly bodies circled the planets. The sun was the center. Solar activity varies on daily, weekly, monthly, yearly, century, and millennium type of frequency. We live in a modern age. And that modern age of observation, recording, and analysis basically only goes back in detail to about 150 years. That's all we have. We go back only 150 years in detail. And in somewhat detail, about 300 or 400 years. But consider, however, that everything has been going on for those billions of years, millions and billions of years. So it's difficult to say what's happening right now astronomically with the sun is unique. It could be critical. It could be cyclical. Every 100 years, every 10 years, every month, every day, and so on. And that is where we start a discussion on the effects of solar activity in our current industrial age. In order to understand the relationship between our weather or climate and the sun, we have to look at solar cycles now. NASA has been looking at solar cycles since the year roughly 1600. From roughly 1600 to 1725, we are what was called a Dalton minimum of solar activity. We did have a maximum somewhere between 1725, or actually 1750 and 1795, then went back into a minimum to about 1800 to 1825. That's what's called a modern maximum, extends from about 1825 right to the year 2000. The highest of which was between the years of 1948 in the 20th century to about 2000. In the 20 years since 2000, however, solar activity has been dropping significantly, closer to what we saw back in the 1600s to about 1725, or at least implying that's what's going to happen. This, in effect, is called a solar shutdown. It's called a solar shutdown. Now, NASA's attempt to paint the upcoming solar shutdown is a window of opportunity. And many of the things NASA is effectively actually forecasting is the return to the Dalton minimum of solar activity that I spoke about earlier. But NASA does not give any mention to what's happened during that period of time. And I'm basically saying that during the 1700s, during that time, there was a brutal, cold period. A crop wash, that's when everything just doesn't work. You plant the crops, they start to go, and then they die. It's a crop wash. Famine, of course, exists because you don't have crops. War and powerful volcanic eruptions. And they imply we're associated with the solar minimum. I'm not sure if the volcanic is, but then again, who knows? The changes in magnetics, the changes in gravity, the changes in everything. It could have something to do with our core of the Earth. There was also that year without a summer, which occurred during the Dalton minimum of 1816. Now, that's 1816. That year without the summer was caused by a combination of already low temperatures plus the effects of the second largest volcanic eruption in 2,000 years. That was being Mount Tamburus eruption on April 10th, 1815. So a combination of solar minimum and volcanic eruption caused very cold temperatures. My goodness, all these things, the sun, volcanoes, all these different trends can actually change the weather so much easier than us driving our car down the highway. But let's go on. It wasn't limited to just weather or change in weather. Earthquakes and tsunamis that followed killed tens of thousands of people living in Indonesia, but the eruption was much of an interest. That Indonesian eruption that happened, the earthquake, then the tsunami that also followed, because a lot of times when you have eruptions, you're going to have also tsunamis, especially if they happen off in the water. But that wasn't much of an interest to Europe and the U.S., not initially at least. Everybody was focused about the wars, in particular the Napoleonic Wars and the border battle at Waterloo on Sunday, June 18th, 1815. That's when the Duke of Wellington defeated Napoleon Bonaparte. And at the time, newspapers were preoccupied with the battle right up until the start of the winter of 1815. The weather concern turned decidedly wacky by 1816, and the climate was dominating the headlines as both spring and then summer failed to arrive. Can you imagine? Not having a springtime, it's just chilly, snow and stuff like that, and then a cooler than normal summer or much cooler than normal. That's what they were dealing with in 1816. Even in the U.S., one Virginia resident recalled that in June 1816, another snowfall came and folks went snow sleighing on the 4th of July. They went down some of these hills. They had snow on the ground. They were sleighing on the 4th of July. Frozen water cisterns and snow fell again, with Independence Day celebrants moving inside churches where hearth fires warmed things a mite. In New England, the summer of 1816, clothes froze online in New England. Ice on ponds and lakes was reported in northwestern Pennsylvania in both July and August of that year. And Virginia had a frost in August. Normally, Virginia has its first frost in November. The temperature occasionally got into the 90s, but then would drop to nearly freezing in just a few hours. That's because the sun is so high, and if you have a nice clear day, the sun will cause the temperatures to rise. Then at night, almost like the desert, the temperature drops back very, very quickly. Now, crops that did manage to sprout were frozen out by early June and replanted and then frozen again in July. Can you imagine? You have to spend extra money to try to replant, and then they die also twice. Very few crops were actually harvested in the summer of 1816. And those that were, the yields were very poor. In turn, food and grain prices skyrocketed. For example, in 1815, wheat sold for about 12 cents a bushel. Now, this is in 1815, the year before this happened. It sold for 12 cents a bushel. The next year, a bushel of wheat be sent you back 92 cents. Well, that's almost 8 times. That's an 8x increase in the price of a wheat bushel. You make bread, make your basic staples from that. You don't have it. Almost $1, 92 cents. That didn't just happen in the U.S., but it's the same all across the world. Now, also, the potato crop in Ireland rotted on the ground, resulting in widespread starvation. And eventually, because of the potato famine, a lot of those Irish ended up coming to America, hoping for a better thing. In England, France, and Germany, wheat crops failed, leading to bread shortages and food riots, and even looting. They were looting because they couldn't eat. Even in Asia, they were affected. Northern China was hit so hard that thousands of people starved to death in northern Asia. In southern Asia, however, it was usually warmer, and torrential rains triggered a cholera epidemic that killed millions. So we're coming up to what's called the solar cycle 25. It'll likely be a mirror stop to our descent into the next grand solar minimum. In other words, we're heading towards a solar minimum. This would appear to have been even further reduced temperatures and crop yields like what they had in 1600s and 1700s. So is that what's going to happen as we go in through the 2000s? This is what's implied through some of the data. But there are scientists and researchers that insist there won't be a cycle 25 at all. They're saying it's not going to happen. Well, excellent analysts from many suggest that all 4 of the sun's magnetic fields will go out of phase in 2020. Others think differently. One way or another, some are predicting that cold times will be returning. It's just a matter of when they'll return. To read everything you can on both sides of the argument so you get a very clear picture of what's happening. This way you'll be well informed. But here are some facts. In South Africa, 14 all-time monthly low-temperature records fell in the 28th of May of this year, 2020. Widespread snow accompanied the freeze, of course, in South Africa. Now, in the northern hemisphere, we're working towards summer. Very quickly now, we're in it. In the southern hemisphere, they're working towards winter. It's getting real cold in the southern hemisphere. So here's a look at the sun. Spotless days are those days where you look at the sun through a telescope and, of course, and a reflector, not directly at the sun. And in 2020, we reached 115 or 78% of the days. Again, spotless days, 78% of the time. We did not have solar cycles. We have to connect how sunspots and solar flares react or influence our weather on the Earth. So when you don't have solar flares, you don't have sunspots, you don't have solar flares, it's going to affect you one way or another. We'll get to that. But so far in 2020, as you know, we've been lower than normal. March, April, May, probably June, at or slightly below normal. The spotless days on the sun have reached 78% of the days so far as of late June 2020. There are a lot of sites out on the internet you can use in order to see solar maximums and solar minimums. The most striking is what shows what happened since the late 18th century through the 19th century, and then more importantly, of course, through the late 19th century for us, right through the 20th, and now into the first quarter of the 21st century. We had a maximum from the 40s to the 90s. Now we're moving towards minimum amount of solar activity. That means sunspots and solar flares. But why is that important? The big question is, how do sunspots and solar flares affect our weather here on the Earth? These are important questions of how these sunspots affect the Earth's climate. If sunspots are areas of energy that deliver more energy into the solar atmosphere than through space, eventually through the Earth, then with the more sunspots and solar flares that we have, the more solar prominences, temperatures on Earth should rise. Can I say that again? If you have more sunspots, if you have more solar flares, solar prominences, it's sending that energy out into space and it gets here to Earth. When that happens, temperatures should rise. What has happened during the late 20th century and early 21st century? Temperatures were rising. Scientific American magazine writes that some of the skeptics of human-induced climate change blame global warming on natural variations in the sun's output due to the sun's and solar winds and solar flares, like we've just been saying. They say it's no coincidence that the increase in sunspot activity and the run-up of global temperatures on Earth are happening concurrently. That happened in the late 20th century. At the same time, sunspots increased, solar activity increased, temperatures on Earth increased. But also, we were industrialized. But we also tried to put the brakes on industrialization, or at least polluting in the atmosphere, and doing things as far as, becoming a little bit more efficient as far as pollution was concerned. Now, the Scientific American magazine writes that variations in solar energy output have far more effect on the Earth's climate than a soccer mom driving an SUV. I'm going to say that again. The magazine Scientific American, which you may or you may not believe is true, but I'm just saying, some people who have been looking at this for a long time, the magazine says that the increase in sunspot activity and the run-up of global temperatures are happening concurrently, and they have more effect on the Earth's climate than a soccer mom, or me, driving an SUV. Something a rational thinker would understand, and especially if he or she had some understanding of the limits of human influence. I mean, are these human beings who we are we really affecting it that much? I mean, basically just by breathing and living, we're affecting everything. So what are we supposed to start doing? Stop living, stop breathing, stop eating, stop waste. Stop and think about it. It doesn't matter what we do. It really matters what the sun does. It matters the most. After all, the source of all energy in our solar system, in our galaxy, and combined with all the suns in the galaxies and the universe, are the energy of life. I know when you chop down a tree, or maybe an acre of trees, and put up a house and a blacktop and some concrete, that's going to change the temperature profiles there. We all walked in the woods on a hot summer's day and felt coolness. We've all walked on the sands of a beach, and the winds were coming off the land, and we know how hot it was and how hot that sand was. These minor changes do make minor differences, but the vast majority of global climate change is bigger than humanity. But sunspots and solar wind are playing a large role in our climate change. So that's where we are. We had a solar maximum of sunspots during the 20th century and are now moving towards a solar minimum. We had a pandemic that's caused a lot of people to go off the roads and not pollute with their cars. We've stayed in our homes and be like most of the cave people of old. The weather has been cool. The sun's activity has been extremely low. What does that mean for the future? The implications are that we are heading towards colder conditions. Again, what does that mean for the future? The implications are that we are heading towards a colder type of climate trend. However, if you believe we're doing it all, the sun has nothing to do with it, then we are doomed to hotter and hotter conditions, like the Twilight Zone episode I mentioned in the beginning. But of course, that's because the Earth was knocked out of its orbit and heading towards the sun, the midnight sun. There are more of us now. Human population greater than there has ever been. We live what is used to be called the life of Riley, as opposed to those who have lived before us. We clear trees, we make farms, we build cities, roads, and everything else that is necessary for modern society. We have made life better. Perfect? No. But we've made it better. We are probably living at the best time up until this point. Things may get better in the future, but up until now, we're doing pretty good. Still, the sun exists. Our star is the number one producer of energy in our solar system. It is one of billions in our galaxy. It is one of untold numbers of suns in the universe, which is comprised of millions, if not billions, of galaxies. Galaxies. Combinations of the Milky Way galaxy. Billions of those. Are we wrong not to care about what we do on Earth? I believe we should take care of Mother Earth, of course. Everybody knows that. Nobody's going to dispute that. But I think that Mother Earth, although being stressed and strained by us, is part of the big picture. The picture of our solar system and the sun, which gives life, which sustains us, which carries in what it gives us, and we live what occurs as that variation takes place. Meaning the changes in temperatures and the changes in climate and the changes in weather are all part of the big picture. We have to take care of Mother Earth. I believe that. Earthers, keep your battle up. Scientists, keep your true information coming in. So keep that unbiased information coming in as best you could. Realists, keep us grounded. I'm a bit of a realist. That's all I'm saying. I think the next 5 to 10 years will tell the story. And we'll know if, despite our best efforts to pollute, consume, and use our Earth, the sun is where we should look at it. The sun will determine our life. Now, thanks for listening. I hope you enjoyed, at least learned a little bit from this. Next time, we're going to talk about the effects of heat and the effects of water and the natural phenomena of water turning into water vapor. Heat from the sun causing rising motion, then coolness aloft, resulting in sinking motion of the heavier, dense air, with the net effect of that making severe weather, severe thunderstorms, tornadoes, with the ultimate of severe thunderstorms. Something we have to consider as we go into the summer months. Despite the fact that whether it's colder or warmer than it should be, that will be our next podcast. And I really want to thank you for listening. I'm certified consultant meteorologist Steve Pelletieri, and I am the Weatherman. Thanks for listening, and have a safe and great summer.